Finish of today's batch of algebra theorems, we shall have a look at the Euler's totient function formula theorem. This is the first theorem whose proof is not trivial, but it is the most interesting by far. We have a lot to look forward to. So without further delay, let's get to it. All right. So what's the claim? Well, if phi is Euler's totient function, then it holds that phi of some integer n is, well, of course, it is equal to the totient of its prime number factorization, whose uniqueness and existence we have already proven. So that's the Euler's totient function of p1 to k1 times p2 to k2 times times pn or m to km. And we claim that this is actually equal to p1 to k1 minus 1 times p1 minus 1 times p2 to, what's happened, to p2 to k2 minus 1 times p2 minus 1 times and so on until we arrive at the last prime number in the factorization, pn to kn minus 1 times pn minus 1. Not entirely practical, because one needs to know the factorization of any given number to use this formula to compute the Euler's totient function, but it is still something, and at least for small numbers this will be much more efficient to use than finding all the totient by hand. As I've mentioned, the proof is non-trivial and is not short, but it's fascinating. So, we need to prove two claims. And these two claims, when combined, will yield the theorem. So, we shall prove the following two claims, which, by the way, are interesting enough on their own to know. So, claim 1. Given any prime number p, phi of p is equal to pk minus 1 times p minus 1, which we can recognize as one of the, twin factors in the claim of the theorem we're proving. And 2, given any coprimes AB, it holds that phi of A times B is equal to phi of A times phi of B. The gentle reader, or gentle listener, surely can understand how these two claims or subclaims give the claim, but in case the gentle reader is inebriated, I'm going to specify. Given any such n as we have in the claim, we shall first factorize it in the argument. Then we shall apply the second claim on the individual factors, or the individual factors with the raised to the appropriate power. And then on each one of the new factors, which will involve phi of some prime number raised to some power, we shall apply the first claim, or the first subclaim, and this will give us the final product. Alright, so proving number 1. This one is easier. So, what shall we do? Well, it is quite simple to compute all the non-coprimes of a prime number. Namely, the non-coprimes, so numbers divisible by p, of prime number p are precisely those elements in the following set. And we will have we are looking for the non-coprimes of the prime number raised to the power of k, and they are precisely the elements which are in the set of p to 1, p squared, p cubed, p to 4, all the way until pk minus 1. But what about the primes? Well, coprimes. Well, we have computed the number of primes, so non-coprimes, so the number of primes must be the total number of options minus the bad options. So p to k minus... Oh, no, sorry. My apologies. Of course, this is all wrong. Of course, it's not the parts, it's the multiples. My bad. So, the non-coprimes of the prime number p to k are precisely the multiples of p. So that's 1p, 2p, 3p, 4p, all the way to p, k minus 1. And here there are p to k minus 1 elements, of course. Since we were going, it's obvious. Thus, the number of primes must be the whole number of options, which is p to k minus 1 times p to k minus 1, which is, of course, there's no minus 1, it's just pk minus 1, which we can write as, if we factor out p to k minus 1, as p to k minus 1 times p minus 1, which gives us the first subclaim, the number of coprimes also. Which gives us the first subclaim. So that was quite easy. But the second one will be a little bit more laborious, but that's where the real fun begins. Alright, so we shall consider the map mu, and it's a map from the set of 0, 1, 2, all the way to ab minus 1. And it maps this set into the set of all ordered pairs of, the first set will be the set of 0 and 1 and 2, etc. until a minus 1 by the set of 0, 1, 2, 3, etc. to b minus 1. and it is given by the following identity. So we define mu to be to map x onto x modulo a and x modulo b. Henceforth, consider the restriction of mu onto the set capital phi AB. That is to say, the set of all totient of AB, or A times B, rather. Then, quite obviously, the domain, or rather the cardinality of the domain, so then the cardinality of the domain of mu is equal to phi of A times B. And now, here comes the beauty of the proof. Get ready. So, we have seen this function before. We have used it in the proof of the Chinese remainder theorem. And we know, we proved it there, that mu is a bijection. So what we shall do is that we shall show that the cardinality of the codomain is equal to phi of A times phi of B. And then since mu is a bijection, they must be equal. The two cardinalities must be equal. The cardinality of the domain must be equal to the cardinality of the codomain. And thus, we shall prove the equality that we want. Quite incredible. It's sort of a backward sort of logic, but it's beautiful. And we shall accomplish this by proving. So, we wish to show that the codomain of mu is equal to the capital phi of A times the capital phi of B times by. Then the cardinality then the cardinality of the codomain is equal to phi of A times phi of B. And how shall we show this? Well, we need to verify two facts for this to hold. So one. So we must verify one. Mu maps the set capital phi AB into the set phi A by phi B. This means, by the definition of capital phi, so this is equivalent to saying which can be formulated as the greatest common divisor of x and a b being 1, implying that the greatest common divisor of greatest common divisor of x mod a and a is 1, and that the greatest common divisor of x mod b and b is 1. So that's the first one. Second one. So essentially the first one simply says that the set is mapped into the correct set. There is an injection going on, but it is not quite sufficient. You also need to show the surjectivity of this mapping. So we shall show that mu maps the set capital Phi AB onto the set capital Phi A by capital Phi B. This is essentially just saying that, so this means that whenever we have the situation when the greatest common divisor of some the greatest common divisor of some number u, some integer u and a, whenever the greatest common divisor of u and a is 1 and the greatest common divisor of v a is also 1, then needfully there exists some x in the domain, so there exists some x in capital Phi AB such that x is mapped onto the ordered pair UV. This essentially says that there exists an x which satisfies that the greatest common divisor of x and AB is 1. But we can obtain both of these results quite easily, actually, if we consider a few equivalences. So, to prove both, we shall observe that now the greatest common divisor of x and a times b being 1 implies, well, we have a biconditional here. This occurs if and only if the greatest common divisor of x and a is 1 and the greatest common divisor of x and b is 1. Both of them must be, neither of them can be divisible by x, because if either of them were, then their product would be as well. But we know by another theorem, whose name I've forgotten, that this is equivalent, this occurs if and only if the greatest common divisor of x mod a, and a is 1, and the greatest common divisor of x mod b, and b is 1. But of course, this is precisely what we wanted. Since we used only equivalence relations, the implication goes both ways, and we have proven both the first and the second point, which proves the second the second big point. And having proven the first big point, we combine the two to give us the claim. And this concludes this rather long, well, it wasn't that long, but this longer than usual proof. And I'll see you next time.